So after the lectures, are you all going through the PowerPoint slides that you have been given in order to connect with the discussion already done? So just try to understand further. So of course, when you come, you would want to go through the slides uh, so that you are having some idea about what will be taught. And then after the lecture, you should go over those slides again. And still, if you have some questions, you can discuss with us, with me or Dr. Sidharth. So yeah, last time we were discussing about pairwise alignment, and we learned about two algorithms that are used frequently in alignment of sequences. One is called global sequence alignment algorithm. The other one is called local sequence alignment algorithm. So if you have to align two sequences so that you can identify the domains in those sequences, then which of the two algorithms you would want to use? Global alignment algorithm or local alignment algorithm? Any thought? So you have two sequences and you want to align those sequences to identify domains. Domains, you understand? Yeah, regions that are conserved over the course of evolution. So you want to identify the domains in those sequences. So which algorithm you would want to use? Needleman-Wunsch algorithm or Smith-Waterman algorithm? Smith-Waterman algorithm, which is a local alignment algorithm, because that will help you identify local regions that are conserved, that are called domains or sometimes motifs. So you would want to use local alignment algorithm to identify domains in sequences. Okay. So we will begin with tutorial. And I will have some lecture also. So we will try to cover a lot of things today. But we will go through the questions one by one. And some of the questions in the tutorial you can do at home. It could be take home homework kind of. But some we can do here because it is just not possible to do all those questions here. It will take a lot of time. So some you can do here. I would come and see how you are doing, and some you can take to home and do there. And next day I will ask how you did. Okay. So let's begin with the first question, which is performing alignment of human beta globin and myoglobin proteins using the Needleman-Wunsch global alignment algorithm, Smith-Waterman local alignment algorithm, and BLAST, and then interpret the results. Okay. So did you all understand the dynamic programming algorithm that we discussed yesterday? We were doing by hand actually, kind of, right? But of course, if sequences are many residues longer, we just cannot do by hand. If you have sequences that are 5 or maybe 10 residues long, then we can do using calculator, we can do it. But for longer sequences, of course, we need to write a program. So you learnt about algorithm, and bioinformaticians like me, they can write program, and so that will implement that algorithm and will get the alignment of the sequences. Could be global alignment or local alignment. Okay. But if you are given short sequences of say 5 or 6 residues, you should be able to do by hand. We learned yesterday, right? The global alignment and local alignment. Okay. So I'm not asking you to do by hand. I'm asking you here to use the algorithms which are already available. So programs, and I think we will find where these programs are available. I think emboss. You can just Google search Needleman-Wunsch algorithm, Smith-Waterman algorithm. You will find it. So I think these are available at Emboss. Check it. Get started with the first problem. And let me know if you are not able to find. I will also try to find these algorithms. And then once you have found the algorithms, you have to get the sequences of human beta globin and human myoglobin. You know how to download the sequences now? So get these two sequences and then use these programs, Needleman-Wunsch algorithm, Smith-Waterman algorithm, and BLAST to align these two sequences. Okay. So first, go to Google and search for Needleman-Wunsch alignment algorithm. Yeah, just Google search, you will find it. And as I remember, it is available at Emboss. So NCBI, it is available at NCBI. I don't know. Is it? Okay. So if it is available, then use wherever it is available. Just use it. So get going. I will come and see. So let me also. Needleman-Wunsch global alignment algorithm. Okay, you can do here also, or you can just. Oh. Okay. Can my computer be connected to internet? Connect. Let's see. I think it should connect. Okay. Yeah, it should have connected automatically. Okay. I don't know this actually. So, okay. Okay. Thank you. Okay. So, yeah, searching for Needleman-Wunsch alignment algorithm. So, NIH. Yeah, there are many actually. Where Needleman-Wunsch. Okay, I will just emboss. Let me see actually. Emboss, yeah. Emboss. Yeah, here it is. So emboss needle. Okay. So go to that. So this is actually Needleman-Wunsch algorithm at emboss. Okay. So here it is. So can you all go to this actually? If you haven't yet found Needleman-Wunsch algorithm at some other site, so you can go here and start with the Needleman-Wunsch algorithm. Okay. Could you? Oh, you did already? No. Oh, what happened?
It's buffering.
Oh, okay. Oh, slow. So first sequence. So paste your first sequence here in this box, first box. Paste your second sequence here. That is the second box. Okay. And then you have to just submit. It's okay. Yeah, it's easy. So yeah, if you have got this, if you are on this site, now what you have to do is to retrieve the sequences of beta globin and myoglobin from NCBI site. So get these sequences from NCBI protein. And then copy paste the sequences in the two boxes and then submit. Okay. So could you? Oh, what's happening? Oh, network. Oh, okay. Let me. Password has been given. Oh, oh, yeah, yeah. Check WhatsApp. It has been provided. Again. Okay. 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 Oh, okay. Very good. So this is global alignment, and what is the? So yeah, look at these values. Percent identity is 22.6%. Similarity is 30. Yeah. So take a note of this, and now do Smith Waterman. So you have to compare. So once you have aligned, you can see the values of the matrix like percent identity, percent similarity, percent gaps, and so on. Okay, because you would want to compare the global alignment of these two proteins with the local alignment of these proteins, and also with blast alignment. So blast is also local, but it is heuristic. These two alignment algorithms, um, the Needleman-Wunsch algorithm and Smith-Waterman algorithm, they produce optimal alignments, the best alignments possible. Okay. Okay. Yeah. Get started, Gaurav and Namrata. So first problem. So I will show you the first problem. Okay. So first problem is uh, yeah, perform alignment of human beta globin and human myoglobin using Needleman-Wunsch algorithm, Smith-Waterman algorithm, and BLAST. So, so you will go to Emboss website and look for Needleman-Wunsch algorithm. Actually, this is called Needleman, just needle here. So, yeah. Okay, anyone else could complete this? Which one? Oh, you did it. Uh, so next you have to get the sequences. You have to get beta globin and myoglobin sequences from NCBI. So go to NCBI. So once you have gone to Emboss site, then you get the sequences from NCBI. Sequence of beta globin, protein sequence of beta globin, and protein sequence of myoglobin. Okay, and copy paste here on these in these two boxes. So you have done it. Okay. Oh, ये भी हो गया अच्छा good. Okay, good. Yeah. So this is okay. Can you go to that? I want to see. Okay. Percent identity about 24%. Percent positives or similarity is 37% gap. So take a note of this, also a score, and then compare with that of the local alignment. So now you will do, okay, you did it. Okay, so can you show me at the top the values of this matrix? Okay, yeah, it seems good. So now perform a local alignment. Okay. Yes. Okay, good. Perform local. Yeah. Done? Okay, good. Okay. Can you show me the parameters? Yeah, the matrix. Okay, it is good. Yeah, you could also. Okay, go to Smith Waterman now. Yeah. Myoglobin and not hemoglobin, beta globin. Beta globin. Yeah, human beta globin, human myoglobin. Done. Okay, good. Now you can do Smith Waterman. Is Smith Waterman done? Okay, show me the values of the matrix, percent identity, and all this. So identity. No, this is not correct. It seems like, yeah, you have to get beta globin and myoglobin. It seems like your both sequences are same. So get beta globin and then compare both. So copy paste. So first box for beta globin, second box for myoglobin. I think there is some error because when you show me and when I will see that it is 100% identity, I know that they are highly diverse sequences. Okay, so see what mistake happened. They are quite diverged, beta globin and myoglobin. So could you do it? So global alignment, good. Do local alignment. Okay, local alignment done. So let me show. Okay, good. This is 24, 39. Okay, so take a note of this and then do blast now. So those who have done Smith Waterman also, they can now do blast. So for blast, just go to blast website and select blast for two sequences. You will see the two boxes that will come. Copy paste your sequences in those boxes and then blast. And remember, these are protein sequences, so select protein blast. Okay. So those who are at the final step, blast, they should do like this. Blast done. Okay. So what are the blast metric values?
थ्रेशोल्ड इंक्रीज किया नहीं तो वैसे नो सिग्निफिकेंट.
Oh no, right. So it is only 16%. Okay, that's interesting.
बट में गैप्स ज्यादा है.
It's गैप ज़्यादा है. अच्छा. Right. It's interesting because those two algorithms give you the best alignment where you are seeing higher identities, right? Blast is heuristic algorithm. So 16% identity only. So yeah, go to blast if you have completed Smith Waterman algorithm task. Yes. Needle is good, yeah. This is Smith Waterman. Let me see. Yeah, this is Smith. Okay, yeah. So take a note of these values and then go to blast. Which one? Oh, you already did. Okay. So yeah, when you do blast, then blast will say no significant similarity found. And I think I discussed this that blast found that these two sequences are not significantly similar because blast uses a statistical significance test. So what you will do, so there is a threshold for that test that is often called significance threshold. In blast analysis, it is referred to as E threshold or expect threshold. So you will look at the top. It says that you can go back to the blast page where you started doing this, and then click on algorithm parameters. and you will see expect threshold, increase it from 0.05 to very high number like 100 or so. So basically you are relaxing the stringency so that the blast will then show you the alignment. So blast will say that, okay, if you want to tolerate this, you have relaxed the stringency, the threshold, so the alignment can be shown. Okay. So by relaxing the threshold, blast should be able to show you the alignment, even though it is not significant. So blast done. Okay. So uh, I think, do you have a myoglobin that is not partial? Yeah, because partial is not good. You'd want to get complete. Yeah, myoglobin, beta, these sequences are completely sequenced. So if you see partial, do not select that. Select the complete sequences. Yeah, otherwise it would not be a fair comparison. You want to have complete sequences of both. Yes.
Explain this again, the last one.
Yeah, right. So, yeah, this change it to high number, 100 or 1000 or whatever you want. Yeah, that's okay. And then it is good, then blast.
So
Yeah.
this is the
Yeah,
watermelon,
this looks good. Yes.
and this is the native.
Yeah, looks good. Yes.
So
Yeah.
watermelon.
This is Waterman 20. And where is the. Oh, what happened actually?
I put the same sequences for
So this is, I think this is not correct, the second one. Can you check actually this again?
this is the
Myoglobin isoform 2 Homo sapiens. Okay, then I think what happened? Okay, go back. Isoform 2. I think this 99, only 99. Okay, let's keep going. Okay, so just type myoglobin. Myo, and then select actually protein, because question is protein. So protein, and then myoglobin. Okay, good. And then Homo sapiens, and not partial. Let's look for complete. Okay, so I see one complete here. Can you use this one? Yeah, not short one. The 154 amino acids. Yes. Okay. Yeah.
so she put the
I think you got it. Yeah.
yeah, I did the e-value 100 and I did this result and she put 1000, she got this. So
No, I think, yeah, it should not happen like this. I think your sequences might be different than her sequences. So can you see the, yeah, because you are using partial, you would want to use complete. Okay, it is possible that both sequences are. So this is NP. This is good. This is Magulis. So yeah, select complete again. Let me see your. Yeah, your is different, right? Yeah, yeah, it happens. Okay, so I think, yeah, you all have made good progress. So you would want to interpret this, okay? And it seems like, yeah, what is the interpretation? You did it. Blast P. Oh,
Only 3 weeks.
only.
22 to 24.
Let me see. Uh,
And I changed the parameters.
okay.
Beta globin,
Beta globin, and then
then my globin,
myoglobin. So what is the percent identity that it returned?
when I am doing blast, only two these parameters.
100. Yeah, that is okay. And then blast. And just let me see actually. Can you show me this? This is beta globin 147 myoglobin. Okay, and come down. Okay, so okay, percent identity is quite high. That's interesting.
Please sir, but तीन ही वो base pair दे रहे हैं
Which one?
alignment पे है ना
Oh, only 3.
हाँ तभी
Oh,
वो
query
system
coverage is only 3. Oh,
coverage.
okay. But you did it. I see that. Yeah, they are beta globin and myoglobin sequences, but there are variants of those sequences. So typically, when I fetch these sequences, I try to get rep6 sequences. Okay, with accession number starting with n. So they are curated. Otherwise, there could be truncated sequences there, and so yeah, we will move to next actually because we have to cover several things. But make sure that when you are downloading the sequences, check if ref6 sequences are available or not, reference sequences. Okay, because other sequences they could be partial, could be truncated. We don't know how good those sequences are. Ref6 sequences are curated by NCBI, NIH curators. So we have more faith on Ref6 sequences. So yeah, you learned about how to align sequences using these different algorithms. And this would be a take home assignment. Given a DNA sequence, ACC and so on. Oh, what happened? Okay, this is just one page. Okay, translate it into 6 possible reading frames. And this is something I will discuss again. I am going to discuss BLAST also today, so I will discuss this. Okay, so then you can do this when you go to home. This question. So there is a DNA sequence. It can be translated into 6 possible protein sequences. Okay, so you will do this later on. Okay. Third question. Explain the motivation behind masking of low complexity regions while performing local alignment with BLAST. Okay. So what I will do is I will start BLAST lecture and then I will come back to this. Yes. Yeah, same sequences. Yeah.
They have different identity results. So
Yeah.
which one should we actually take out of this?
Yeah, right. So it depends on what you are interested in. For example, if you are interested in identifying local regions that are conserved, you would want to use local algorithms, Smith-Waterman algorithm and BLAST, right? And of course, then you would want to select the algorithm which gives you the maximum value of identity, right? Because the goal of these algorithms is to maximize the identity or similarity between two given sequences. What could be the maximum level of identity or similarity that you can get when you align? So this is the goal.
So
Okay.
out of these three, I have the highest with water, so I will take this one.
Yeah, if you are interested in local alignment, then you would want to say that, okay, I'm going to use this because this is optimal alignment algorithm and it is giving higher similarity or identity value. So I'm going to use this for this problem. Okay. Okay. So so I will start with BLAST so that you can come to these questions later on. So I will close this. Yes.
I use the other sequence now, which
Yes,
is
right.
but still, like, I'm getting 0%.
Still?
Yes, I don't know why.
Oh, and this is
The other one is fine.
okay. So this is hemoglobin beta. Okay, protein. Protein. Yeah, make sure that you select protein when you are doing Needleman or Smith-Waterman. Okay, So at emboss site, it seems like it is coming by default DNA. You have to change it to protein because you are aligning protein sequences. Okay. So make sure that if you are aligning protein sequences, it should be protein option selected there. Okay. Otherwise, it will not return you anything. It will be no alignment. So, okay, so let's get with started with BLAST, and then I think we did this. So, realistic models I will do later on. 6. Okay. Okay, so yeah, these algorithms were great. The Needleman Wins algorithm and Smith Waterman algorithm, because these algorithms were able to give the optimal alignment, the best alignment that is possible between two sequences. Okay. But still, they were computationally very demanding as the database grew further. So, database of DNA and protein sequences, it was really a challenge to perform the comparative analysis because they were still very slow. Despite these algorithms being dynamic programming algorithms. So, for long sequences, it was just not possible to use these algorithms because of the computational challenges of using these algorithms. So, people also started thinking about developing algorithms that may not give optimal solution, but may give close to optimal, suboptimal, and they could be really very fast. And those solutions could make biological sense. Then why not use those algorithms, because they are really fast and they will give you biologically meaningful results. So, one of such algorithms in biology is BLAST, and BLAST stands for Basic Local Alignment Search Tool. It was developed in 1990. Actually, the paper was published in Journal of Molecular Biology in 1990, and since then it has garnered hundreds of thousands of citations. So, you can check the BLAST citation. So, it is one of the most used algorithms in biology. So, BLAST, which is Basic Local Alignment Search Tool, allows rapid sequence comparison of a query against a database. It is fast, accurate, and web friendly. Okay. So, what you can do with BLAST? So, you will start thinking about, okay, I want to do sequence analysis. So, what BLAST can help me with? So, you may have some problems in your mind. So, just give me some examples where you can use the BLAST, for what purposes? I'm sorry? Yeah. Which gene it is? So, which gene it is related to? Okay, there is a known sequence. So, if it is hitting with 100% identity to some sequence, then I will say that, okay, this gene is this one. So, you will name it, right? So, unknown will then become known. So, you will put a name over your gene. So, okay, that's one example. Any other examples? Why you would want to use BLAST? Comparative genomic, of course, comparative is more specific. So, in comparative genomic studies, for example, you want to identify homologs, right? And when you think about homologs, then you may also think about orthologs and paralogs. So, you want to use BLAST to identify homologs and paralogs, sorry, orthologs and paralogs. So, yeah, BLAST has been frequently used for identifying orthologs by biologists. They are very interested in identifying orthologs in different organisms. So yeah, it is a very useful, very fast tool for that. Otherwise, you may have to make phylogenetic. You remember we did phylogenetic tree yesterday, and we tried to annotate homologs as orthologs and paralogs. So one can do like this, but there are other ways. They are fast. They give solution, which is also okay, which is also good. BLAST is one such algorithm. Okay, so identifying orthologs and paralogs, identifying new genes. It is possible that the sequence that you have is a gene which is not yet identified. So which means that when you blast against database, you will not get any sequence with 100% identity to this one, your query sequence, right? But if this is a gene, it is likely conserved, so it may get a hit, maybe 90%, but then you will say that, okay, I have found a new gene. Yeah, and it is homologous to this particular gene, the hit that you will get in the database, right? So you will find a new gene using this approach. Discovering variants of genes and proteins, same thing actually, variants. You would want to know the variants of, for example, beta globin gene in humans, right? So BLAST will help you in identifying variants of beta globin in human individuals, and so on. There are many. EST we already discussed. Okay. So here are the components of BLAST. You have to choose the sequence. So your sequence of interest, that is called query sequence. You will select BLAST program. You will select the database that you would like to search in, and then choose the parameters, then click BLAST. Okay, so I did all this for you, screenshots. We'll not go to a BLAST page at this moment. You have the screenshots, and so that I can go fast. So this is the first box is the query sequence box. So you will copy paste your query here. You can also just enter the accession number of the sequence. Okay, you don't have to copy paste the entire sequence. Accession number is sufficient. And then the database. So most often you will select the standard database, the non-redundant database of sequences. And then so is this BLAST P? Okay, so this is protein BLAST, and then program selection. So there are many different BLAST variants, actually, you can say, for protein analysis. Okay, so you will select BLAST P unless you have reason to select some other BLAST program. Okay, so BLAST P is protein BLAST, and others are also BLAST for protein comparisons, but often you would select BLAST P. We will discuss why you would want to select other BLAST programs in a moment, okay, for protein comparisons. And then you will BLAST. Okay, so let me. Oh, it is hanging. So, okay, yeah, it did. Okay, yeah, I don't know suddenly. Okay, good. Okay, so then BLAST. The first step is choose your sequence. So the sequence can be in FASTA format, and now you understand FASTA format, right? You can go to the NCBI or EMBL or DDBJ and get the sequence in the FASTA format. FASTA format is the format for continuous string of letters that denote nucleotides for DNA or denote amino acids for proteins. That's FASTA. Okay, so here is an example FASTA. So you will get the FASTA and then run BLAST. So you can, I think there is an option to run BLAST from NCBI website directly. You can run BLAST here. Okay, so BLAST comes in 5 flavors. And they are BLAST-N for nucleotide BLAST, comparing DNA to DNA sequences. BLAST P, which is protein BLAST comparing two protein sequences, and then translated BLAST, and they are also used for protein comparisons. So we will learn about these in a moment. So here they are. So if you have a DNA sequence as a query sequence and you want to compare with a DNA sequence in the database, then you would want to use BLAST N, which is nucleotide BLAST. Okay, so there will be one comparison, one DNA, query DNA, and one subject DNA. Okay, from the database. Okay, protein BLAST, which, and all these are actually, which I am going to discuss further, all these are protein comparisons. So BLAST P compares query protein with a protein in the database. Okay, so protein to protein comparison. So one comparison. Okay. BLAST X, the query is DNA and the database is a protein database. So you want to compare DNA that you are interested in, your sequence of interest, with a protein in the database. And DNA is a different polymer than protein. You cannot make comparison directly, right? So, but you know that DNA makes RNA, RNA makes protein. So you know that DNA can be translated to proteins, okay? And we will learn in a moment that there could be 6 possible protein sequences arising from a DNA sequence. Only one would be real protein. But 6 possible protein sequences from a DNA sequence, just in a moment. So which is shown here, 6 possible, and compared with a protein in the database. So how many comparisons? 6. And the fourth one is you have a protein sequence of interest with you, and you want to compare it with a DNA sequence in the database. Okay, so you will then translate the DNA sequence in the database into 6 possible proteins, and then do the comparison. So how many total comparisons? 6. You could have DNA sequence and you want to compare with a DNA sequence in the database, but you want to compare at protein level, right? Because you believe that when you will compare at the protein level, you will see the conservation that you may not be using DNA, because DNA, you know, evolves faster than protein, right? So that's why you want to translate these 2 DNA sequences into protein sequences, so that you can assess the conservation at the protein level. Okay. So then 6 possible protein sequences from query DNA and 6 possible protein sequences from subject DNA in the database. Okay. So 6 multiplied by 6, total 36 comparisons. Okay. Okay, so let's get to the 6 possible protein sequences. So here is a DNA sequence at the so this is double stranded, so 5' to 3', and you know that the complement. So A complements with T, right? So if you know one strand, you know what the second strand is. So here it is. So you want to translate this into 6 protein sequences, but it is possible that you don't know which codon position is C situated in. Okay, you are given this, and how many codon positions are there? Codon is a string of how many nucleotides? 3. So how many codon positions could be? 3. 3. So okay, but given a sequence, you don't know which codon position is this situated in, right? So let's say that this is situated in position 1. So then this would be position 2, 3. So this would be first codon. Okay, and then second codon would be CAA, CTA, and so on. So this is shown here actually. So CAT, then CAA, CTA, and so on, right? So then you will use the standard genetic code table to translate it into the first protein sequence. The second possibility could be that, okay, not CAT, A is in first codon position, okay. So then it would be ATC, right, ATC, and then AAC, and then so on. So this would be the second protein, okay. And then the third would be that, okay, it is likely that T is situated in codon position 1, okay. So then this would be TCA, ACT, and so on, okay. So only 3 from this, because there are only 3 codon positions, okay. So you got 3 proteins from here. So similarly, so you will read it from 5 prime to 3 prime. Now the other strand, complementary strand, you read from the other direction. So this is 5 prime, this is 3 prime, okay. But you will do similarly, you will say that, okay, this is first position, codon position, so GTG, and then GGT. So where is it? Here, GTG, GGT. This is the first. So this is on the complementary. So this is number 4. We got 3 here. This is number 4. Okay, so you can also think of the other scenario where T is situated in codon position 1. Then the 5th protein sequence can be obtained from this sequence of codons TGG, GTA, right, and so on, okay. And the last one, so G is situated in codon position 1. So then the codon would be GGG. So this is 1, this is 2, this is 3. So GGG, TAG, and so on. GGG, TAG. So 6 proteins. So you can translate. So this is a question in your tutorial. You can do at home. Translate into 6 possible protein sequences. Now you understand. You should be able to do it. Okay, good. Okay, so the third step is choose the database, and often you would choose the non-redundant default database, but sometimes you would want to explore more. And there are refseq databases, so sometimes you would want to select refseq. Okay, you can see refseq options. In protein also you can select refseq. But before selecting other databases, make sure you read about those databases. Which sequences are archived there? Which sequences are there? You would want to know before you select the alternative databases. Okay. Okay, so select the database, which is actually, this is the option, the standard database. Otherwise, you will get here the option to choose any other database that you want to. Okay, so which is here. The organism that you want to compare against. For example, you want to compare against only human sequences. So you will write here in this organism box human or Homo sapiens. Okay, you have the option to exclude also. You don't want to compare against human sequences. So you will select this exclude. So it will exclude human sequences from the database. Okay. Okay. So and then algorithm. If you want to do protein blast, then you have many different options. The default that comes with is BLAST-P, and actually yes, you can select all these are translated BLAST, but when you select BLAST-P, you will see all these options. Most of the time you will be using BLAST-P, but I will discuss today also about SciBLAST and why you would want to choose SciBLAST. It's really a very good program for protein analysis. Okay, and then you will blast, it will show you the results. Okay, so when you click on algorithm parameters, and you did actually when you were doing the first problem, then you will see all these different parameters, and you would want to understand what these are. So maximum target sequence is 100. This is just for display. It will show you 100 top hits only. Okay. If you want to see more, then increase this value. It may go up to 10,000, I think, or so. So you can check it. The expect threshold, it is like significance threshold, which is 0.05, and in statistics most of the time people use 0.05 or 0.01. So I asked you to change this because when you did comparison of beta globin and myoglobin, it returned no significant hit. And so I asked you to just relax this stringency so that BLAST will show you the alignment. And when you looked at the alignment, it was very low similarity, just about 16% or so percent identity. Okay, and then there is a word size. I will explain this in a moment. The scoring matrix. Now I think you will appreciate what these scoring matrices mean, because we just discussed about these matrices. PAM matrices and Blossom matrices. The default is Blossom 62, and I mentioned yesterday that this is kept default because this can identify close relatives, and it is also good for moderately distant sequences, distant relatives, moderately. But if they are really quite distant, then you would want to use matrices like PAM number, PAM 250, or BLAST 45 or lower number BLAST, right? So you will get some options here. When you just scroll down this, you will see the options. And then gap costs, now you understand. Gap existence or gap creation -11 and gap extension -1, right? We discussed about this. There are options, other options also you can select. And of course, sometimes these are established based on just large scale comparisons. They may not be mathematically established values. Okay, so after large scale comparison, these values have been established for you, so that you can use the default, and you can also check with other values which are provided here. Okay, good. And then filter, mask, and one more thing is here, compositional adjustment, conditional compositional score matrix adjustment, and this is for atypical genomes. For example, the genome of Plasmodium falciparum. Have you heard about Plasmodium falciparum? Okay, so the genome is quite atypical. I think over 80% of the genome is A or T. So it's very low GC genome. You can check actually. I'm just trying to recollect. So it's quite atypical. If you look at genome, it will look like mostly A or T in the genome. So, and when you will use the standard scoring matrix like Blossom or PAM, remember these matrices have been derived from sequences of all proteins actually that were considered, all protein families. So it's a summary statistics over all proteins that were considered. However, when you encounter atypical genome like Plasmodium falciparum, because you are using a matrix that is a general matrix that represents all proteins that were considered, so that matrix may not be appropriate for atypical sequences. They are good for most of the sequences that have GC composition that are not such extremes, like Plasmodium falciparum over 80% ART. Okay, so because of that reason, when you use matrices like Blossom and PAM for atypical genomes, the results are not going to be good. And for these regions, compositional adjustment for these matrices have been done. So there is a theory on this. There are papers published. So when you will select this, what it will do is it will scale the values of the standard matrix by some factor. It could be some constant. So there are many different ways actually to do scaling. I'm not going to go into detail of that, but this is just to help you understand that by doing compositional adjustment, the matrix becomes good enough for comparisons of atypical genomes. Okay, so if I will ask you a question, then you should be able to explain why compositional adjustment. And then the other parameter that you would want to consider is filtering. So filtering low complexity regions. So low complexity regions are repeat regions. So for example, A is repeating several times. So in DNA sequences, it's a repeat. In protein sequences, some amino acids could be repeating. Sometimes two amino acids repeating multiple times. So these are low complexity regions. They are present in so many sequences, and the alignment may just happen because of the presence of these repeats, not because of they sharing a common ancestor. Okay, so you will get hits that are not homologous because of the presence of these repeats, because these repeats will result in alignment, significant alignment, but they have nothing to do with homology. Okay, so you would want to mask these low complexity regions, these repeats, so that the hits that are returned are not just statistically significant, but they are biologically significant also. Okay. Okay, so all these you now understand, and this was for protein blast P, and this is for blast N. So it's similar. It's similar, except that the match and mismatch score, because Blossom and PAM matrices are used for protein alignment. Okay, for DNA, the values are, for match it is +1, for mismatch it is -2. Okay, so this is actually, I think, a standard, but you will see some options that you may want to select, and so on. I think we discussed this. So these parameters are optional. It comes with default setting. So, but you have the options. You can change these parameters, but unless you are expert in this field, you would want to use default. Okay, but if you want to get more into this, then you would want to learn about these parameters and how changing these parameters can help get you better results. Okay, so and you are doing all this, so you will do again the tutorial questions. You already did beta globin and myoglobin. So at the top you are shown the query name, and then this is the blast search output top portion, and the program name. So if you use blast P, it will show here the database. This is non-redundant database, and so on. You will also get an option to see multiple alignment of hits. Okay, and so on. And bottom page you will see the hits. These are the hits. Okay, and then there is this is descriptions of the hits, and then you can click on graphical summary. So you can see the graphical summary of the hits. So at the top you are shown the this is, I think, beta globin. So beta globin from here to here, and I think total 147 amino acids, and these are the hits. So you can see that the first few hits, it's like 100% query coverage. So query coverage is okay. So this was about the domain actually. So the query span is here from 1 to 147, I think. Okay, beta globin, and you can see that many of the top hits they cover almost 100% of the query. But later on, some are not, some may be just 97%. You can see that at the start, there are no matches actually here, some portions of the start. So this will help you in assessing these hits, and these color coding indicates the scores. So red color means greater than 200 scores, so which would indicate highly significant hits. Okay. Okay, so alignments. So when you click on alignments, you can see the values of these metrics that you did actually in the tutorial, the first question. Percent identity, percent similarity, percent positives, and so on. So now you understand these method, compositional matrix adjustment. So why compositional matrix adjustment would have to be done? Because why you would want to do compositional matrix adjustment? Because genome could be atypical, right? So you would always want to select it if it is not selected, but because you may not know actually whether your genome is atypical or not, right? So it will not hurt if you will select it. It will always be okay, and I think by default it comes selected, and that's why actually it is showing here. I may not have selected it, but you have to understand. You understand percent identity, you understand percent positives. So what is the difference between percent identity and percent positives? What is the difference between percent identity and percent positives? Percent positives is same as percent similarity. Okay, so what is the difference between percent identity and percent similarity?
Similarity also has close related proteins.
No,
Amino acids that are
amino acids that are mismatches in the alignment. So two amino acids that are aligned, they are different, they are mismatches, but they get positive score values because they have similar physicochemical property. Okay, so they are replaced often in course of evolution because their replacement does not disrupt the function of the protein because they have similar properties. Clear? So percent positives include identities and mismatches that get positive scores. Clear? That is also percent similarity, same thing. Percent positive, percent similarity, same thing. And gaps you understand. So now if you click on taxonomy tab, then you will see the hits in different taxa. And this is beta globin in human, the query. So you can see hitting in primates and so on actually. It will hit in many different taxa. But the top ones, of course, here are primates. The sequence was human sequence. So you would want to see the taxonomic grouping of the hits by clicking on taxonomy. Okay. Okay, good. And then, okay, you understand this. So, high score values means high E values or low E values? Low E values, right? Because high scores means more significant, likely more significant, which would indicate that the E value, which is analogous to P value, should be low, should be small. As small as is the P value or E value, the more confidence you have that the result is significant. Okay. Okay. So, and now I think you understand this, so I don't have to get to this. So, you know global alignment, you know local alignment, and BLAST is a heuristic approximation to local alignment. Yeah, it does good job actually, and that's why so many people are using it. Even though it is not giving you the best solution, the optimal solution, it does a good job. So people are using it quite frequently, and it is really fast. And here is the central idea of the BLAST, but I think rather than reading it, you may not be able to understand this. I would show actually how BLAST works. So let's consider a query protein, human retinol binding protein, and here is a part of that protein, FSGTWYA. Okay, this is the query protein. And let's consider a query word GTW, but let's get all the 3-letter words in the query sequence, and that could be FSG, FSG, SGT, SGT, GTW, GTW, TWY, WYA, right? All possible 3 words from the query sequence. So this is the query sequence, and let's focus on query word GTW. So if there is a GTW in any of the sequences in the database, then it will hit it, because that would be exact match, right? It will hit it. On the other hand, you know that sequences evolve, so you would want to tolerate some mutations, okay? And if you tolerate one mutation, then you would consider, for example, ATW, which is just one mutation at first position of this word. This you may also consider as a hit, because you are tolerating one mutation, okay? Similarly, GSW can also be a hit. This is also one mutation. So this is done similar to what actually I just explained. So GTW hitting GTW, you will compute the score for this. So GTW aligned to GTW. So you will look in the Blossom 62 matrix, what is the score for G aligned to G? So G aligned to G, and that should be on the diagonal 6, okay, 6, and then T aligned to T. So T aligned to T 5. So 6 plus 6 plus 5, W aligned to W gets 11. So 6 plus 5 plus 11, 22. Okay. Now you are having a tolerance of one mutation. So let's consider all words with one mutation. So GSW. So G to G is 6. TS is 1. So you can go here and see TS. So T and then S. Where is S? Here, 1, right? 1. So 6 plus 1 and W is 11, 18. ATW, so similarly you will do 16, NTW 16, GTY 13, and so on. But then a threshold has been put. So those better than the threshold will be kept. So these one highlighted in yellow, and those that are worse than the threshold will be discarded. Okay. So these will be hits. So which means that when BLAST encounter these hits, so GTW aligned with a GTW in the database, it will be hit. And then what BLAST does, it extends in the either direction. So it extends the alignment in the either direction, and it pauses when the score for the alignment falls below a threshold. Then stop. Remember, this is local alignment. Okay. Okay. So this is how BLAST does. This was the original version, but in the later version, BLAST requires 2 independent hits, not 1, 2 hits that are in close proximity to each other. Okay. So this helped minimize false predictions. So it became more specific. So the requirement was that there should be 2 hits, not 1, in close proximity to each other. Okay, so we'll skip this. This is when you increase the threshold value, then the number of hits and extensions will increase or decrease. Decrease, right? Because if you increase this, there would be fewer hits, so fewer extensions. So which is this one? So this is shown here, and for BLAST and nucleotide BLAST, the word size, now you understand. I showed you the algorithm parameters where word size was mentioned. Okay. Now you should appreciate what word size means. Okay. In nucleotide BLAST, the word size is longer. So it could be 7 nucleotides, 11, 15, or even more. So when the word size increases, will there be more hits and extensions or less hits and extensions? Less, because it will become more specific, right? And that is why the mega blast, which uses the word size 28, is really very fast. Okay, so it is important to assess the statistical significance of your blast results. You get a hit and you would wonder how significant the hit is, whether I should accept this as a significant hit or I should just discard it. Okay, so mathematicians and of course many other people have worked on this problem. For global alignment, the statistics is still not well understood, but for local alignment it is. So you would want to see the distribution of scores from alignments of random sequences. So sequences may get aligned just by random chance, not because of relatedness. What are the scores for those? Make a histogram, get the distribution, okay? And that distribution you can use for assessing the statistical significance of a value of the similarity score that you will get when you are analyzing your sequences, okay? So and now you know about normal distribution, standard distribution, right? So it follows the distribution for a score from local alignment follows extreme value distribution. So you can see that with the normal distribution, which is this, the tail decays faster, right? Decays more sharply than with the extreme value distribution. You can see that. So extreme value distribution is a well studied distribution, and this is considered in many different disciplines actually. Even in physics, uh, I was considering this this distribution in the context of some problems in chaos theory. Well known, and this helped in assessing the statistical significance of blast results. So this led to development of a statistics which is called e-value statistics. Okay, so e-value, expect value, e-value is the number of hits in the database with a score S or higher. So you got a score when you aligned myoglobin and beta globin, you got a score, and I will say S. So let's say the score is S, it has some value. So and then that will return some e value for you. So then that e value is the number of hits in the database with a score S or greater that just happened by random chance. Okay, and that's why you would want to minimize this, right, as low as possible. So this is expect value definition. So number of hits in the database with a score S or greater that happened just by random chance. Okay. So an e value is related to p value. We will see the relation in a moment. And here is the e value relationship with the score. Okay. So S is a score. M and N are the length of the sequences, two sequences. Lambda and K are Carlin-Altschul statistics parameters, named after two scientists who developed this statistics. Okay, so as you can see that if S is very large, then E would be. If S becomes very large, if score is very large, then E would be 0, or you will say it's very low, right? So as S becomes larger, E becomes lower. Okay, good. Okay, so here is the relation between p value and e value. Okay, this one, and then comparison. So when p is 0.00 01, so 301, E value is also the same. When P value is 0.0487, which is close to 0.05, E value is also 0.05. Okay. When P value is 0.9995, E value is 10. Right. So you would not want to consider this one when you are assessing the statistical significance, right? That's very high E value. So, but earlier BLAST had a default of 10. Now they have changed it to 0.05. So, which means that now because the database is more enriched, and maybe for some other reasons they keep changing this actually. So now the threshold that BLAST uses, the default threshold, which makes more sense than what it was before. Okay, so now you understand this, but if you will click on search summary, so you did all this BLAST analysis with the two sequences. So you might have come to this page, click on search summary, and then here is the search summary, and this will help you in getting the different metrics or parameter values that were used, the algorithm parameters. Word size 5. Now you understand word size. Okay. Okay. Expect value you understand. Default is 0.05. Hit list size. So this is the display size. So only 100 hits will be shown in the graphical display. Okay. If you have selected, so this is default actually 100. You can increase it. Gap cost you understand. Matrix you understand, and filter string F. This is some code. So you want to filter repeats. So there could be some codes for filtering. So that is F here. Genetic code 1 I think is a standard. So a standard genetic code is indicated by 1. Window size 40. 40 means that the two hits should be 40 nucleotides or amino acids away from, not more than that. Okay, so that is the window size. So that is the limit. Threshold, you remember threshold? That was 11. Now they have made it even lower actually. Threshold is 0. So there would be now more hits and extensions, right? Because now I think computer has become really fast. So they are lowering it down because of the power of computation now we have. Okay, and then size of database and so on, and these are the parameters of Carlin Altitude statistics. These are the constants actually. Yes, question? No, okay. Okay, BLAST search strategies. So you would want to evaluate the significance of your results, how to handle too many results, how to handle too few results. And these are some challenges that you face when you do BLAST analysis. For example, you begin with retinol binding protein as the query sequence, and then you got these hits. And if you look at the bottom, there are hits to PAEP, and PAEP is, okay, I can see here better, progestogen associated endometrial protein. This is a placental protein 14. Okay. So all these are lipocalins, retinol binding protein, and all these hits are lipocalins, but PAP gets a E value, a score of 0.49. So E value is 0.49, and then complement component 8 gamma, that is also lipocalin, it gets E value of 1.1. So if there is a threshold of 0.01 or 0.05, they will get discarded, right? Even though they are lipocalins, they are right hits. So sometimes people wonder actually how to solve this problem. One approach is to perform reciprocal BLAST. So the whole idea is actually, I will skip this. The whole idea is that if retinol binding protein hits apolipoprotein B, all are lipocalins. So these are, retinol binding protein may hit apolipoprotein D first because they are closely related, but it may still hit, but the E value will be higher with odorant binding protein. Okay. So what you will do actually, and then you will wonder whether I should include odorant binding protein in the list of homologs of retinol binding protein or not, because E value is high. So what you would want to do is start with odorant binding protein as the query and then do BLAST. And if it is a homolog of retinol binding protein, then it should also hit apolipo D, and then it will hit this but with high E value. But because this hit this first and then this also hit this first, because of the association you will say that okay, they all belong to the same family. Some are close relatives, some are distant relatives, right? So this is a approach developed by biologists, not mathematicians who developed BLAST. So because biologists are the users, they are really creative. They think how to make it more biologically helpful, a useful tool. Okay. Okay. Yes. Yeah. You can. Yeah. If phylogenetic tree, you can make phylogenetic tree of this protein family. Yeah. You can make it. But remember, even when you make phylogenetic tree, you want to identify homologs, right? And then you want to perform multiple alignment. So it is important that you include all real homologs and exclude spurious homologs. So this may not be done by a mathematical program. You may have to intervene actually. So you may have to apply biological insights to do this. Okay, that is why there is always collaborations between the developers of the program and users of the program. Otherwise, these programs will not become this famous if there is no such collaboration. How to differentiate, and that is what I said, that there is no program actually that can say with certainty that these are true homologs, because evolution happened so many years ago and it has been happening, right? These are not observed, these are inferred. So no 100% certainty that any two sequences are homologs. But we can say actually, so if two sequences have say 99% identity, then you have very high confidence that they are homologs, because that level of identity just cannot happen by random chance, right? So and that is why when you use BLAST, then you obtain hits. It doesn't mean that those are homologs. It just gives you highly similar sequences. Homology is inferred based on similarity. So two sequences can be very different, maybe just 5% identity, like random sequences, but they can be homologs. They might have shared a common ancestor that existed billions of years ago, and they have diverged, and they have become so different. They are homologs, but these programs will not return those as homologs. So false positives or false negatives, false negatives, right? So so there are challenges actually, but we have to actually wade into this and try to address this. I'm sorry?
Can you solve this kind of problem in the future with more coding?
Coding, yeah. I think at some point, and now artificial intelligence and all this, we are becoming better in inference than before, but there are still very much challenges there, because here at least we know everything of what we are doing. With more sophisticated models like artificial intelligence models, we sometimes don't understand how that model come to such a great solution, right? And that is why right now the challenge with artificial intelligence is its interpretation. which is a new field actually now emerging out of this. Unless everything about what a model is saying is understood, it may not be accepted by society or some sections of the society. Doctors may not accept such a medicine which is not fully explained. AI will give you a medicine, but it will not be able to explain how it get to that medicine, right? How it got to that. So, and yeah, so there are challenges, and scientists, me as well as all of you here, you all are PhD students or faculty members. You are working hard to make these models interpretable, so that they can not just give great solutions, but one can also explain why they are great, why they have yielded these solutions. Okay. Okay. So yeah, let's keep going because we have some problems to solve in a moment. Okay, so we did this. So, and this is the problem which you just did, aligning beta globin with myoglobin. And when you did this, it returned no significant similarity. Then you change the parameter expect threshold value to 100 or 1000 or whatsoever, and then it returned the alignment with 16% identity. Okay. So this is a problem with BLAST P, that it is not able to align. It does align, but it is not able to return myoglobin and beta globin as homologs, or yeah, we often say homologs, and I just said that yeah, BLAST is not for predicting homologs. It is just predicting whether the sequences are similar or not. But I think this is happens over the course of time. We start misusing actually the concept. So BLAST is not good for comparing. BLAST P is not good for comparing sequences that have evolved a long time ago, that are highly divergent or highly dissimilar sequences. We need some different program. Okay. So, and that different program is SciBLAST, which we will learn in a moment. Okay, so limitation of BLAST. So, one limitation we just learned. The other could be longer sequences like genomes. Yeah, it would be really hard to compare genomes using BLAST. Variants of BLAST have been developed that can align longer sequences. For example, BLAST Z, BLAT, MEGABLAST, Pattern Hunter, and so on. So let's consider SciBLAST and see how SciBLAST does in aligning myoglobin and beta globin. And this could be your homework actually. Not here, you can do later. So the whole idea of SciBLAST is to derive a matrix that is tailored to the query that you begin with. Okay. So if you have a query of beta globin, then you would want to derive a matrix that is customized to beta globin, which means that a matrix that represents the family that beta globin belongs to. And beta globin belongs to the family globin. Globin. So when you will use beta globin as a query, then you will get hits to globins first, right? Because there is a large globin family, so the BLAST will try to pull in all those other globins when you use beta globin as the query. So, and I think great that when you do this, BLAST is able to pull in the members of a protein family that the query sequence belongs to. So people started thinking that, okay, why use BLOSUM 62 or PAM, which is a matrix that represents summary statistics over all different protein families. Can we derive a matrix that represents globin? And if we can, then use that matrix when you are using beta globin as a query, right? So this was the idea. So very simple idea, but it worked. So start with beta globin as the query. You will get hits expecting mostly to the globin family. Then use those hits to derive a matrix. Okay, and then use that matrix for blast of beta globin against the database. Okay. Okay, so let's see how it is done. So the first step is start with a query and search it against a protein database, get the hits, and then make a multiple alignment of those hits. And this is called position specific scoring matrix. Okay, once you made multiple alignment, then you can derive a matrix from that multiple alignment. Okay, I will show you in a moment how. And that is called position specific scoring matrix. And again, I will show why it is called position specific scoring matrix. And then, so let's see actually. So I started with some query sequence and then got hits. And those hits were aligned. So this is multiple alignment. Pairwise alignment only 2, multiple alignment more than 2. It means more than 2, not more than 1, more than 2, multiple alignment. Okay, so you can see the hits. And these all belong to a family that the query sequence represents. Okay, and there are patterns actually. You can see that some columns have only RIK substitutions. Okay, on the other hand, this column has only C, cysteine. So cysteine is conserved, completely conserved in this column. And then DET substitutions, KRT substitutions. So if you look at this multiple alignment, basically you are trying to assess the conservation at different alignment positions, right? So that is why it is called position specific, because you immediately start visualizing the patterns at different positions. And that's why this is called position specific scoring matrix. The matrix that is derived from the multiple alignment, that is called position specific scoring matrix. So you can derive the matrix using the same formula that we discussed. You remember the formula? The score. A score is 10 multiplied by, yes, log base 10 Q AB PAB, right? PAB. Okay, good. So the same formula you can use to compute these values. But here you are going to, so I'm going to show you actually what this is. So this is query sequence on the side, M, K, W, VW and so on. Last residue is A. So query is 42 amino acids long. Okay. On the top are 20 amino acids. There are total 20 amino acids. They are shown at the top. Okay. Okay. And now you are going to consider each position. So for example, if you consider this position, then you would want to compute the score for this position. Okay. And a score for each of the amino acid aligned with other amino acid and of course aligned with itself also. Okay, you would want to compute this, but you would compute for each of the columns. So for example, if you consider this column, then consider all pairs, all possible pairs. So H aligned with H, H aligned with H, H, all pairs. And it seems like this is mostly H and Y. So if there are 90% HH pairs, so 90 out of 100, okay? So total pairs 100 and out of 100, 90 are HH. So what would be QAB? 90 out of 100, so that would be 90% and that is 0.9, right? So value of QAB would be 0.9. And then in the denominator, you have by random chance. So you can just randomly reshuffle this, okay? And then repeat for that column. And what you will get, you will put here in the denominator. This ratio is likelihood ratio. Take the logarithm of this is log likelihood ratio. and this is also called odds ratio. Okay, so as the score is actually odds ratio, you have computed the score, which is shown here actually next, which is shown here for each of the positions for the alignment of two amino acids. Okay, so amino acid for position 1, amino acid M aligned to A, M aligned to R, M aligned to N, and so on, right? This is query. So that is why this matrix is customized to the query, okay, and it represents the family that the query belongs to. So this becomes really customized to that family. It is representing the peculiarities, the characteristics of the family that the query belongs to. And that is why you would expect that this matrix should be now sensitive in identifying even distant homologs of that family, right? Because of that reason. Blossom 62 may not, because it doesn't represent this family, but this should be, because it represents this family, and those peculiarities or characteristics are represented in this matrix. Okay, so that you can see actually. So if you, for example, if you look at the score for A aligned to A at position 6, it is 5, position 11 5, but position 14 3, position 15 2, so it varies based on the position. So that is why this is called position specific matrix. So it has more information that represents the patterns specific to that family. Okay, and similarly for the tryptophan. So this matrix is used by SciBlast for identifying homologs of a query of interest. So okay, let's get to this. You can do this. You can start with SciBlast. So you can do with the you did beta globin, and do not select myoglobin as a subject. Select the database. Okay, and then you would also want to select ref-seq here, because NR would be, and I will show you actually. I have the screenshots. I will show you that. Let's get to that. You don't have to do actually. I have a screenshot, but even if I provide you a screenshot, you should repeat it. Do on your own. Otherwise, you will not learn. Okay. Okay. So let's look at this. So what SciBlast does, it goes through iteration. So in the first iteration, it will make the first matrix using the hits that it will get. Okay, and we'll use that matrix to find the homologs. And I will show homologs, don't worry actually. Okay, we keep saying home because this is easy to understand. So you will get homologs or you will get hits, you can say hits also, and then use those hits to refine the matrix. Okay, so first you will make the matrix using hits, then you will do blast, you will get new hits, then use those all hits to make matrix again, repeat it. So this way you are continually refining the matrix, continually changing the matrix as you are getting more and more members of the family that the query belongs to. Okay, at some point you will say that the query, this process may have found all members of the family, so no new hits will be returned. Okay, but if it works, then it should have found not just close relatives but also distant relatives of the query sequence. Clear? Okay, let's see. Let's see. So, and this is human retinol binding protein, and this is from the book actually. So, human retinol binding protein as a query. Database is ref-seq. So you can see the query is retinol binding protein, and complement component 8 gamma is worse than the threshold, and threshold is, I think, is 0.05. Okay, in the first iteration. In the second iteration, the E value improved from 0.07 to 0.01. So it got included. Sequence with E value better than threshold. So threshold, I think, say 0.05. So it got included. Okay. So next iteration, iteration 3. So you can see now the E value for complement component 8 gamma is 10 power minus 34. Improved quite dramatically. Okay, so it seems like this is a powerful model for identifying distant homologs. Okay, so a retinol binding protein matching with ApoD, apolipoprotein D. Iteration 1, E value 10 power minus 7. Iteration 2, 10 power minus 42. Iteration 3, 10 power minus 34. So don't worry, it is not going to always decrease. It is just adjusting. As new and new members are being added, these are getting refined, so this value will change. It is still close to 0. So iteration 2, 10 power minus 42, 0, almost 0, and this 10 power minus 30 is still 0. But it will keep getting refined as you keep refining the matrix through this iterative process. Okay, so yeah, I think we discussed this. The universe of lipocalins, each dot is a lipocalin, and when you use retinol binding protein as the query and use PAM matrix or Blossom matrix, it does identify the homologs, but mostly closed homologs. When you use SciBlast, then it is able to identify distant homologs also. So it's not like going in circles. It is like really capturing the universe, just a cartoon. Okay, to help you understand that it helps identify distant homologs. Okay, so this is what I did for you, and I think you should repeat. And I think you should repeat for beta globin and myoglobin. Okay, so you want to see if when you use SciBlast, myoglobin is returned by SciBlast as hit or not. But use the RefSeq database, and it's better to use the organism Homo sapiens. So you will select actually organism here, Homo sapiens, because let's focus on the, otherwise you will get so many hits. So you want to find the homologs of retinol binding protein in the human genome. You would select the database RefSeq, and this is the first iteration. So in the first iteration, which is the simple BLAST P iteration, BLAST P, you get how many hits? Only 5 sequences. So SciBlast first iteration is using Blossom 62. So it is the regular BLAST P, okay, that returns 5 hits. So now these 5 hits will be used to make a position specific scoring matrix, okay, and this will replace Blossom 62. That will be in the second iteration. So second iteration, how many hits? So from 5 it increased to 11, okay, and these 6 are new hits. So now they will be used, they will all be included in constructing the position specific scoring matrix, okay, and then that will be used for doing the BLAST. So in the next iteration, from 11 to 21, so 10 more got added, okay. So keep repeating it because you want to identify all homologs of retinol binding protein in human. Okay, how many are there? So far we identified 21. I kept doing it actually. I wanted to see how many. Iteration 4, 30. So from 21 to 30. Iteration 5, 41. Iteration 6, 44. I didn't go further, but maybe it will add 1 or 2 more. So which means that, okay, by doing this, I have identified the homologs of retinol binding protein in human, and it is about 50 or so. I didn't do, but you can check it, okay. It is about 50. So you can see that by doing this, you are able to kind of exhaustively identify all possible homologs in the human genome, homologs of retinol binding protein, which the regular protein BLAST program, which is BLAST P, will not be able to. Okay, so this is the power of SciBlast, And if you are interested in such kind of problem, then you would want to use SciBlast. And one of my students actually who completed PhD, I think 3 years ago, he was earlier using SciBlast, but when I taught him this actually, that okay, try this, he started using SciBlast and he got really good results. I think he published 2 papers using the results he got from the usage of SciBlast. So of course he was doing more than that. He was studying phylogenetics, but using SciBlast helped him really make good trees. Earlier he was not able to because of the inability to identify the homologs of the sequences that he was interested in. Yes. Which one? What? Oh, what is changing? Oh, the matrix is changing. So, for example, if you go back actually iteration 5, so iteration 5 you got all these hits, right? And now these new ones are also added in making the position specific scoring matrix. So now the matrix will change. Now the matrix is represented by even more members of this family, right? So the matrix is becoming more and more refined towards the family that query sequence represents. So now a new matrix that will be used, so you would expect new hits, right? And it did return few new hits because of that reason. Then you refine again, you will include these in making the new matrix, position specific scoring matrix, okay? And then repeat it. So at some point it will saturate. So all members of the family might have been identified. But one of the problems with SciBlast is corruption, which I will come in a moment. But how to validate SciBlast? So SciBlast is a powerful method for identifying distant homologs, which means that you would want to consider proteins that are less than 40% or 30% identical, but their structures have been solved, and when those structures are superimposed, then there is a high similarity at the structure level, okay? So which means that, okay, likely homologs, even though less than 30% identity at sequence level, because structures are so similar, they are likely homologs. I am now saying putative homologs are likely homologs because we cannot say with certainty homologs. Okay, so such a list of proteins were compiled, and then they were used for testing SciBlast. That is SciBlast able to identify those proteins or not as homologs? And indeed it did, and that's why this was included in the BLAST suite of programs, okay? So, but one of the issues with SciBlast is the corruption problem, and the reason is that when a hit is included, it always remains. So even in the earlier rounds of iteration, if a hit is included and if it is a spurious hit, it remains there ever. And it is possible that a spurious hit may draw many other spurious hits that are similar to it. So that will corrupt the BLAST results. Okay, this is called corruption problem. So for example, and these are coming from biologists. So Dr. Jonathan Pevner is a neurobiologist who wrote the book Bioinformatics and Functional Genomics, and we had some good conversation. So yeah, he actually suggested many examples from biology, and I think which are very interesting. So a query with a coiled coil motif may detect thousands of other proteins with this motif that are not homologous, because this motif is so much ubiquitous kind of. Similarity could be because of the presence of this, not because of they sharing common ancestor, not because that they are homologous, right? And the goal often in the sequence alignment is to find homologous sequences. Okay. Okay, so there are ways to address the corruption problem. So you would want to apply filtering of biased compositional regions, which we discussed. You would want to adjust e-value, make e-value even more stringent. You don't want to include any spurious hits, so make it more stringent. So for example, right now default is 0.005, make it 0.000001. So you will get fewer hits, but yeah, you will have more confidence that they are really good hits. Okay. And if you are expert, then visually inspect the output from each iteration, remove suspicious hits by unchecking the box, because when it is checked, it means that they will be included in making the position specific matrix. So you can uncheck if you are expert, then they will not be included in deriving the position specific scoring matrix. Okay. Okay, so what people have done, they have made position specific scoring matrix for each protein family. So now there is a database of position specific scoring matrices representing many different protein families. Okay, CDD, conserved domain database. So you can have a query sequence, and then you compare the query sequence against the database of models, and those models are position specific scoring matrices of different protein families, and determine that which of these models is the best match to the query. Okay, the best match will be the protein family that the query belongs to. Clear? So this was BLAST. So we should come to the tutorial questions. So next question in the tutorial. Okay, where is that? Okay, so let's get to the next question in the tutorial. Okay, question number 3 in the tutorial is explain the motivation behind masking of low complexity regions while performing local alignment with BLAST. Anyone? Question number 3. Yeah, just think and try to answer. What did you say?
Sure that the hits that we are getting are due to the significant alignment, not because of the repetitive sequences.
Oh, not because of the.
Repetition of sequences.
Okay, so yeah, so when you mask, then yeah, you are getting very good because of they sharing a common answer. You should say like this, because they sharing a common answer. Yes,
So this would basically mean that they are actually homologous.
they are actually homologs. Yeah, they are likely homologs. So yeah, it is actually uh, uh, yeah, it's certainty. We don't know actually. These evolutionary events are always inferred. They are not determined. Okay, so be careful, and we also misuse often, but I think yeah. Okay, question number 4. Which is explain the effects of changing the algorithm parameters on BLAST results. For example, what happens when you change the word size? I think you answered that question. So when you increase the word size, more specific. So fewer hits, fewer extensions. Okay. Question number 5. Interpret e-value in BLAST analysis. So I say that e-value is 10. Okay. What it means? Yeah, you can speak a bit louder because No, why E value 10? So what 10 means? No, what 10 means? Yes.
The probability of switching the sequence with by random chance is more as compared to actual their
What 10 means?
10
E,
times more.
no, 10, E value 10. Okay, I will say again. Okay, I will say the definition of E value. Try again. Okay, try again this. No, no. So E value is definition. E value is the number of hits with a score S or greater in the database search that just happened by a random chance. So when I said E value 10, so 10, now put 10 replacing E value. So 10 is the number of hits with a score S or greater. So you have two sequences and you got a score S, okay? And you also got E value 10. So, and you want to interpret. So 10 is the number of hits with a score S or greater in the database search that happened just by random chance. Clear? Clear? So 10 means that, yeah, you got 10 hits actually that just happened by random chance. They are not homologs. Clear? So that's why you want to reduce this. Okay. So next question. Why is psi blast considered more efficient than regular protein blast in identifying members of protein families? We just discussed this. Why is psi blast considered more efficient than, not that, than regular protein blast in identifying members of protein families? Okay, so why psi blast is able to identify distant relatives? Right. Matrix position specific matrix. Okay, yeah, very good, you are getting the point. So yeah, you would want to say that when you use psi blast, the matrix that is used in the blast becomes customized to the query, which means that it represents the family that the query belongs to. And because of this, it becomes more sensitive in identifying members of a protein family and thus likely the distant relatives of the query protein as well. Okay. Remember, psi blast is only for protein comparisons, not DNA. Okay. This is option for only protein. Okay, very good. Next question. Explain the problem of corruption with psi blast and how it can be addressed. What is the corruption problem in psi blast? Weak interactions. Why that could arise? Okay, yeah, good. Yeah, yes, yes. Yeah, so in psi blast, all previous results are frozen, they are included, they are ever there. And the problem is that even if there are a few hits which are spurious, they will ever remain there and they may bring in more spurious hits that are similar to them. This is a corruption problem. So it is important that you keep taking out the spurious hits in the iterations of psi blast so that you have the results that are more vital, that are more reliable, right? Okay, so next question. Protein searches are usually more informative than DNA searches. Do a blast search using retinol binding protein 4, restricting the output to arthropoda insect. Now do a blast and search using retinol binding protein nucleotide sequence. Select only the nucleotides corresponding to CDS, coding region of DNA. Which search is more informative? How many database searches have an E value less than 0.001 in each search? Can you get started with this? Solve problem number 7 and get started. I will come to you and see where the things are. So, you have to get the sequences as being asked. Retinol binding protein, accession number is given. So, you can just input the accession number, you do not have to, but remember in retinol binding protein nucleotide sequence, you have to find the coding region. So, you will have to go to NCBI to get the coding sequence and then perform the blast, nucleotide blast and protein blast. Okay, get started. You don't have a computer? No. Oh, okay. Yeah. So you can't solve on phone. It is difficult. Okay, going well. Uh, okay, so yeah, this question actually, question 7, you would want to do a blast search. So go to blast protein blast web page. Yeah, you would want to go step by step. So open a new tab. You can keep it. Yeah, open it. Yeah, click on plus, and then type blast p, because the question is saying do a blast p search. So type blast p, Google search blast p. Blast p, that's okay. So protein blast, this is blast p. Click on this, and then accession number is given. Uh, okay. Okay, so accession number is you can see here actually, if you are having, or I think you have the print of all this. Oh, yeah, then you can use that. Yeah, it is there. Okay, good. Yeah, you can use that. So accession number is given. So you can just type the accession number. Yeah. And remember, you have to restrict to arthropoda. So organism is arthropoda.
Error.
Which one?
Error message.
Okay, why? So did you?
Yes.
Can you enter the accession number? No, don't exclude actually. Yeah, you remove that, exclude. Yeah, you have to include arthropoda. Yeah, type arthro. It will come. Okay, this should. Yeah, it should come. Oh, organism type there. Okay, retinol binding protein. Restrict the arthropoda. Okay, this restricting organism. Yeah, it should come already auto populated, so you can select here arthropoda. Okay, tax ID is 6656. So you see, then the search will be limited to arthropoda only. Okay, so this is what the question is saying, that you have to restrict your search to this organism only, and then blast. Okay, do it. So at least, yeah, did you do first? So how many hits are there? Uh, Protein total. Oh no, no, yeah, this is only for display. So there could be more. So increase the hit list size. Okay. So again, sometimes you will want to tinker with algorithm parameters. Here I am asking you how many hits, and of course you would want to when you want to address this problem. So you have to change from 100 to maximum that you can have here. Okay, because 100 is the just display size, there could be more hits. So just change it to the maximum that is possible given there. Okay. So let me know how many hits with protein blast. Oh, still searching. Oh, okay. Okay. So while it is searching, why not you get an why not you go to NCBI and get a coding sequence for this one, and then perform nucleotide blast. Coding sequence for retinol binding protein. Oh, you have got it. Okay, so once you have got it, then you have to do nucleotide blast. So okay, which one? Yes, yes, but this is going to give you messenger RNA actually, but from that you have to get coding sequence. Okay, only coding sequence. So coding sequence will start with the start codon. For eukaryotes, almost always ATG, and will end with one of the three stop codons, TAA, TAG, and TGA. You got it? Okay.
So TTL is bit less than 0.00.
This is DNA.
This is daily.
Oh, using coding sequence. So you get 7 hits. Okay. Okay. And how many of them are so lower than point? What was the question? 0.001. Oh, none. Okay, but these are hits. That's fine. Okay. Yeah, looks good to me.
How to look at that?
So number of hits, to increase that, you have to go to algorithm, go up, edit search, edit search, and then go to algorithm parameters, go down, algorithm parameters, change it to maximum. Maximum target sequence is 100, change it to 5000. 5000 maximum. Okay, so change it to 5000. Okay, this is the maximum. Default is 100, and then do blast, and let me know how many hits you are getting when you are using the retinol binding protein as the query, restricting the search to arthropoda. So how many total hits for protein blast? How many? Oh, 667. Okay. Okay. So note it down, 667. And then do nucleotide blast as instructed. How many?
Expected threshold we have to increase. Expected threshold we have to increase.
No. Don't eat this one. Maximum target sequence. Yeah, let keep it actually as it is. Just increase to 5000. Yes. Yeah, and keep it 0.05. Okay, anyone? Actually, there, yeah, one answer I got, 667, right? For protein blast. Others also 667. Okay. You got more? 1000. Okay, so let me see how you did actually, because maybe you are right, but I don't know. So, how many you got? What happened? Compare. So, okay, so you zero. Oh, so if you select actually, oh, it is still doing. Select all. How many sequences are there total? Let it come actually. It is still going. So, yeah, show me. Okay, so can you go back, and then I will. I want to show from see from the first step. Okay. Uh, okay, but you have not restricted to arthropoda. So type here arthropoda. Question was restrict to arthropoda.
So DNA was suddenly coding sequence.
I think that is yes. I heard from other person also 7. So I think it might be the right result. That's why you have to answer the next, answer the question accordingly.
Which has a more informative.
So which one give you more results? Yeah. Did you? Oh, you are doing again. Okay. Let's see what comes. And did you change this to 5000? The algorithm parameters.
Yes, sir.
Oh, you have changed it. Oh, you are doing.
But DNA sequence.
No, but you have to first get the coding sequence.
Yes, sir. I got so.
Where is the coding sequence? Yeah, but this is messenger RNA sequence, not coding, right? Or this is coding?
Coding.
Oh, you got the coding.
Position specific.
Oh, that's fine. That's fine.
667.
Oh, you got it. Okay, 667. Oh, it seems like an. I think. What's your name? Chandramani. Okay. So yeah, Chandramani has got a different result. So we are trying to figure out why he got a different number. Because it's like a conversion 667 for protein blast, and nucleotide blast 7 hits only when CDS. So how many hits you are getting? Nucleotide 667. Oh, and nucleotide blast. So did you get what happened? Oh yes, yeah. Go up actually. Go up so that I can see what's going on. Yes. Nucleotide. No, this is protein actually. So yeah, so you cannot have this is protein actually. You cannot do blast, and for blast and is only for nucleotide. That's why it failed. So, but first do the protein blast. So select blast P actually, as question is saying, and then this is good, and then go down. So this was the accession number, right? And then arthropoda is good, and then algorithm parameters, you increase it to the maximum 5,000. It's good. Then do blast.
Sir, I did the CTS.
Yeah. How many you got? Oh, you got more. Okay. Yeah, it's close. I don't know. I will have to look at why there is discrepancy, but I think I will trust that. Uh, did you restrict to arthropoda?
Yes, sir.
Okay.
This is the CTS.
Oh, now you are doing CDS.
This is CTS
The,
faster.
the 800 something that you showed is from protein blast, right?
No, sir. This
DNA?
nucleotide.
Oh, no, no, there is something wrong. Can you show me the steps? Go to blast page.
Sir, I did it from here only.
Oh, okay. No, no, do from blast page because uh, yeah, go to blast and then blast web page and then nucleotide blast. So, oh, you got it. This is the right answer. So, can you do the second part? Get CDS and then so not so the accession number is given for messenger RNA. You have to get the CDS from there. Yeah. Okay, yeah, do it, and I think
Yes.
others are reporting only 7. Okay, 7. Okay. Oh, 6 is, so what was the problem? Arthropoda was not selected. That was the problem. Okay, okay, done, done. Okay, yes.
What is the meaning of E value coming this way? It's 9E dash 3.
Oh, so 9 multiplied by 10 power minus 9. This is what it means. Okay. Okay, so it seems like you were able to do it, which is good. Uh, the protein blast hits total 667 and nucleotide blast 7. So can you answer the question now? Which is more informative, protein blast or nucleotide blast? Protein blast, because you are getting more hits. So that's why you would want to use protein blast because protein blast can help identify more homologs because of protein evolving slowly. So more signals there, conservation signals, longer look back time, and that is why more hits were returned. Okay. Okay, good. So I will skip the next question. Go to the last question. Next question is for your homework. Which one? Oh, question. Yes, question. Okay. So question number 8 I am skipping, and I am asking you, when you go back to home or wherever you are staying, you try question number 8. Then that is also pairwise alignment. I want to do you to do a psi blast question, which is question number 9. Okay, so try. It's simple actually. I want you to try psi blast. Question number 9. Okay, question number 8 was also psi blast, but that's fine. I think 9 would be easier, but let's see. So try 9. Namrata, try it. So accession number is given. So you don't have to copy paste sequence. If accession number is given, just put accession number and then do whatever is being asked. If it is psi blast, do psi blast. If it is blast P, do blast P. It's very straightforward question. Just do it and let me know. Done? No? Okay. What's happening? Okay. Starting? Running. Oh, running. Okay. Let me know if you run into a problem.
Then how many times to do it?
Yeah, generally 5, but go to 10. Yeah, let's see. Yeah, I think 10 is good. So last question going on well? Done? Oh, very good. How many? Oh, oh, it's still running. Yes.
I could not get that coding result. Coding sequence, not coding.
Could you get coding sequence? Could you? Coding sequence.
Previous one?
Yes.
Yes, sir.
Okay, can you show? Show them. Yeah, you have friends sitting here. I think they can help. So go to that NM, right? Accession number. It will show you the information about that and look for CDS. This is what you did, right?
Click on this video.
Click on the.
उसका नीचे fast आएगा उसी में जरूर first
Answer.
definition बनाती है.
Oh, okay.
Sir,
Yes. Which one is it?
last week.
Oh, okay. So protein. Now do psi blast, but 100 you would want to change it to the maximum. So hit.
5,000.
Yeah, 5,000. Yeah. Otherwise, it will always return 100. So make sure you change the maximum target sequences from 100 to the maximum, which is 5,000. when you are doing such analysis. Okay, otherwise it will always return you 100 hits. You want to see as many hits as it can be returned. So going on well. Oh, it's still going on. Oh, okay. So after you have done a blast P, do psi blast. 500. Oh, okay. Oh, okay. Your psi blast takes time. So let me see actually. So the previous question you definitely want to try at home. It's also psi blast. Psi blast takes time. That's why we cannot do all these psi blast problems here. So we are trying one here. You can do the other at home. And tomorrow when you come, then I will ask whether you were able to do or not. Question number 8 here. You got it? How many?
500, so it's 8 division 3.
Number of sequences. Oh, you okay?
Again, if I do again, because previously also it was 500.
Okay, so yeah, keep repeating and try to answer the question that is being asked. What is the question? That when you look at the taxonomy report to see which viruses match this query. Next, repeat the search using several iterations of PSI-BLAST. Compare this taxonomic report to that of BLAST-P search. What do you observe? Are there any non-viral sequences detected in this PSI-BLAST search or not? Okay, of course you would expect viral hits because you have started with the virus sequence, right? HIV1 pole. The question is asking, are you also getting non-viral hits? Okay, so when you do this, you have to look at taxonomic reports and then answer this question whether you are getting non-viral hits or not. What? Oh, you are getting those hits? Okay. Okay. Oh, you are getting this problem. So you are not getting this problem, right? She is getting some. You also got this problem.
So what to do after this? Like in the taxonomy report.
Okay, then go through. Then see if you are. Oh, you are getting.
This is for blast P. We are also getting. This is cyber.
This is Cyblast iteration 1 and gag pole, and you are getting hits too. Yeah, no, taxonomic report was okay. Drosophila, oh no, this is so you are not getting hits to viruses. You are not getting hits to viruses. That's interesting. Okay, so let's try actually. Let's try. Okay, so okay, so this is HIV pole and okay, blast P and then remember you have changed all these things. Yeah, they are coming. Yeah, make sure that you have changed all these things from the previous gag pole and non-redundant, which is okay. Blast P, this is okay. 5,000. This all looks good. Okay, so this is just blast P. So you have done blast P. Can you show me the taxonomy report of blast P? Not psi blast iteration 1, blast P.
For blast P,
This is the taxonomy. Oh, yeah, these are all viruses, right? Okay. So yeah, yeah, that's why it was really surprising to me. So this is psi blast iteration 1, and you are not getting hits to viruses. So yeah, this is what I'm trying to check actually. You see, blast P, you are getting all the hits to viruses. So yeah, it is slow actually. Yeah, it takes time. Okay, I think the problem is with the psi blast. So let me actually, in the interest of time, let me try psi blast. Psi blast. Okay, this one, the standard. No redundant protein sequencer. Okay, at this point, I will, because of the time, I will change it to refseq. Okay, from non-redundant, I am going to change it to refseq. And then okay, this is good, good, and good. Maximum target I will make it 5. Oh, 20,000. Okay, and all this is good. Yeah, let's do one thing actually. Maybe open in a new protein blaster. So just blast p. Okay, good. And then psi blast. And then algorithm parameters I'm going to increase to maximum, and all are good, and then I will blast. Okay, let's see. Yeah, so yeah, I just changed from non-redundant database to refseq, because refseq is a small database, so I should be getting fast. So let's see. I will get less hits, but it will be fast. Yeah, this is how you have to handle these things, and this comes with experience. When you are having problem and when it is taking more time, you are going to change the database. So I changed from non-redundant, which is a large database, to curated database, which is a small one, RepSec. And then I will see the taxonomy report, because some of you are reporting only non-viral hits in the taxonomy. So I want to see what's going on. Yes. Which one?
वो जो सेक्टर से फिल आउट
ऑर्गेनिज्म में आर्थ्रोपोड पहले से एंटर
वो आर्थो इसीलिए ऐसा हो रहा था। वो हम भी जो है जब उसमें डाले थे तो आर्थ्रोपोडा था, तो हम उसको डिलीट किया। कैंसिल, देन यू रिपीटिंग, repeat it. Yeah, so the reason actually it happened because it was arthropoda before and it remained there. Delete it. Do not restrict to arthropoda. Okay. Yes.
So now I have to compare this other side.
Right. You have to compare the blast P taxonomy report with the psi blast taxonomy report. Yeah. Now you are getting. Oh, sorry. Oh, you are getting it. Okay. So now we were able to address that issue. So look at the taxonomy report for each of the iterations and compare. You reported that with blast P, when you look at taxonomy report, you are seeing mainly viral hits. You are not seeing non-viral hits, right? When you are doing psi blast, each iteration, check the taxonomy report and see what you are getting. Are they all viral hits only, or you are getting non-viral hits also? So you are doing that? Okay, good. So how many iterations have you done? How many iterations you have done? Oh, so you restarted. Okay. How many iterations you did? Oh, okay. Okay. Oh, I got it. Okay, I got it. So this is first iteration, and let's look at the taxonomy report. It is still. So I see all viral hits actually when I'm just looking at it. It is still going through all these retrovirus. Okay. Virus. Okay. Okay. Okay, so taxonomy report. Oh, still not. Oh, okay. You got viruses now. Oh, okay, good. Okay, so I would let you all now go to home or wherever you are staying and run it. Actually, it takes time, but you can do it. Both question number 8 and 9, and let me know. Okay. Yeah, one suggestion actually for last question is that because of the large database of virus sequences, if you use non-redundant database, then it will keep giving you viral hits for so many iterations. Okay. You would also want to try RefSeq, as I am doing. RefSeq database. RefSeq is curated, and it is also non-redundant. Of course, more the NR database is non-redundant, but RefSeq is even more non-redundant. Okay, curated single copy kind of reference sequence. So you would want to try that also, and it will be fast because of the small database that RefSeq is. And then let me know tomorrow the results that you got with question number 8 and question number 9. Okay. Okay, then we'll see you tomorrow morning at 10, right? And Dr. Sukla is not here. He is traveling. Tomorrow he will come in the evening. So I will do Dr. Sukla's, which is whatever when it is 10 to 11 or whatever the time is, because I think he covered what he had planned to cover tomorrow. He already covered today, right? So so I will do my topics in all 3 or 4 sessions.